So let's go ahead and do the calculations that are associated with changes of cuts or changes of planes or changes of coordinate system. They are all equivalent expressions of what we are trying to do. So now to do this, I already drawn pictures that are intrinsically 2D in the previous example, and therefore we want to at the start focus on 2D scenarios, which are technically referred to as plane stress. And we have to keep this in mind. Now, plane stress means that there are only stress components that are associated with two axes that we choose. Or if you choose the third axis, the stress associated with that third axis is identically zero. So for instance, if I'm choosing a plane stress that is associated with the xy directions, then the third direction is the z direction, and the stress associated with that z direction is going to be equal to 0. And those stresses can be normal stresses or shear stresses. That's the definition of plane stress. Now here, my plane refers to the xy plane, and therefore the third direction is the z direction. Those stresses are 0. So we have a plane stress associated with xy. So therefore, we're going to look at a picture where there's sigma x, sigma y, and tau xy. The plane doesn't have to be the xy plane. It could be the yz plane, and then the third direction would be x. Or it could be the xz plane, then the third direction would be y, right? And anything associated with y would be 0 then. But let's just focus on one case, and if we know how to work with one case, all the other cases eventually follow in a similar manner. All right, so now because we are making this assumption and because we have chosen as a convention to begin with the xy coordinate system, what we have is a picture that looks like this. So we have a sigma x, we have a sigma y, we have a tau xy, and goes without saying that we have the same quantities on the other surfaces. Okay, so I'm not writing tau yx, tau xy, they're equal. They are on different planes, they're in different directions, but the values are different, so I'm just writing tau xy to indicate that. Okay, so that is the picture that we see, the state of stress at a given point in the structure. Let us always remind ourselves, so I'm imagining that we have a loading. The loading might be 3D. Plane stress refers to a scenario where the stress state is intrinsically 2D. So we might have a loading. Let us say that we have some torque and maybe some axial stress, and I'm looking at a point here. That's the point I'm looking at. And at that point, let's say there is a state of stress that looks like this, which is a plane stress state. Okay. So now that state of stress is expressed with respect to the xy coordinate system. Now at the same point, what I want to do now is answer the question, well, if at the same point I take different cuts, so in other words, if at the same point I choose that geometric representation of the element, small chunk of material, oriented in a different fashion, if that is my choice, and that choice is associated with new directions, let's say an x prime direction and a y prime direction, then we've just discussed that the stresses I measure, the components, the state of stress is the same, but at that point, the way we quantify the normal stresses and the shear stresses, their values will change. So therefore, I will have a new normal stress, sigma x prime. Okay, that's the way I will indicate it. There will be a new normal stress along the y direction, y prime. And there will be, in general, new shear stresses. But still, tau xy prime will be equal to tau yx prime to satisfy equilibrium of moments. And so that's the way the picture is going to look. Okay. And now the question is, suppose I give you this, or suppose, right, for a given state of loading, typically the axes, the orientation of the structure dictates what these choices are. Say, in this case, let's say the x direction is the axis of the cylinder, and so it's clear what I should choose it to be. But now I'm interested in the question, if I had chosen it to be some other direction, then how would the components of the stress change at the same point that I am looking at? All right. So to answer that question, what we're going to do is we're going to concentrate on a surface, and we're going to essentially do an equilibrium of forces to find out the components of the stress. I know these from the original loading through my usual equations from 231, but this is non-trivial because the orientation of the axes are non-trivial, and therefore this is the challenge here, to find these new components, okay, given the values of those. So I'm going to, let's say, concentrate on that surface. Okay. And I'm going to take that surface and notice that it's a surface that is oriented at a certain angle with respect to the original surfaces, and I'll put it on that picture. I'll superpose it, okay? And, well, the critical thing to observe here is that with respect to the original axis, there is a certain angle here, and let's call that angle theta, that characterizes the orientation of these planes, okay? And I'm choosing theta to mean the orientation of that plane, okay? Now, the orientation of that plane and that plane is going to differ by an angle of pi over 2, or 90 degrees, right? I'm referring to this angle to indicate the direction associated with the normal to this plane, okay? So once I take that, place that surface on that picture, I'm going to take that chunk of triangle and I'm going to draw it over here again, okay? So that's the way the triangle looks, okay? So I have two pictures. The two pictures are equivalent in the sense that they are describing the same state of stress. It's just that the orientation of the planes are different. I know the values on that picture. That's what I've said. So here I know the value of sigma y. I know the value of sigma x. I know tau xy. But I don't know sigma x prime, which lies normal to the surface, and I don't know tau xy prime on the plane with x prime in the direction y prime, tau xy prime. Okay. Now, this is a chunk of element that is supposed to be in equilibrium, right? So eventually, when I do a force equilibrium, then I should be able to figure out the components sigma x prime, tau xy prime, because they should be such that the sum of the forces acting on this small triangle is eventually equal to 0. Now, to do that, I need to assign some dimensions. Let us call this to be of unit length. So this is length 1. If this is 1, now notice this is theta. If this is theta, this here is also theta. Okay. And therefore, this angle or this distance over here for a unit length, that's what I've assumed for convenience. Really, it could have been some arbitrary length, but everything's going to be scaled by the same value eventually. So I just called it 1. So this is sine theta, and this here is going to be cosine theta. Okay. Now, the thickness along the vertical direction is likewise something we're not going to be concerned with. It's an arbitrary thickness, but that will scale everything that we do, so we assume that that thickness is, if you like, also 1. So now we do some of the forces. along the x direction, which is that direction, should be equal to 0. That's one constraint. And the other constraint is that the sum of the forces along the y direction should also be equal to 0. Okay, so, well, let's go ahead and do the sum of the forces along the x direction. Now, first of all, on that plane, there is sigma x prime acting. So sigma x prime, but that's stress, that's not force. We have to multiply it by the area. It acts on an area of length 1 and the thickness is 1. So 1 times 1, the area is 1. But the angle, the orientation is not along the x-axis. So I need to take its component along x. And that is a cosine theta, because if theta is 0, it's along the x-axis. So the area is 1, but the cosine theta takes into account the component of the force along the x-axis. So that's along positive x-axis. And then along the negative direction, there's a sigma x acting on a plane with area cosine theta times 1. Okay, so the thickness is again 1. And there is also tau xy acting, this one, which is again minus tau xy. And eventually it is acting on an area of value sine theta, again thickness is 1. And finally, we also have to go back and recall that there's a shear stress here, that is tau xy. So I'll write that underneath here. And that will contribute to a negative value minus tau xy prime, acts on an area of 1, but now its component is going to be sine theta. If theta is 0, it does not make a contribution to the sum of the forces along the x direction. So that should be equal to 0 as a sum. Now then, if I go and do the same thing for y, well, there will be a contribution to the y force from x prime, so that's going to be sigma x prime, this time sine theta. And likewise, there will be a shear force contribution, which is now positive, plus tau xy prime. The area is 1, but the direction should be this time cosine theta if it's 0, if it's in the vertical direction. And then there will be a contribution from sigma y, so minus sigma y. The area is sine theta times 1, again unit thickness, and then there will be a contribution from this tau xy, minus tau xy multiplying cosine theta. Okay, everything should sum up to 0. Good. So now, once you do those, now I have two equations for two unknowns, right? And those are well defined. You just have to do some manipulation and try to go ahead and extract the value of sigma x prime and tau xy prime from these two equations, and you will find that the result is the following. So sigma x prime is going to come out to be, and in your book, if you like, there should be directions eventually to complete this derivation, but you can easily do it yourselves as well. Sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. Okay. So then there is also a tau xy prime, which is equal to minus sigma x minus sigma y over 2. So this minus multiplies everything. Sine 2 theta plus tau xy cosine 2 theta. Okay. All right, so those are the values that we solve from these two equations. Now, therefore, what I've been able to do is I was able to start from the at a point, I have the state of stress expressed with respect to default planes or default coordinate system. This is the original coordinate system. And now I'm trying to find the components of the stress at the same point. So the state of stress is the same, but the components will change because the coordinate system is oriented in a different way. Or in other words, I'm taking cuts that are oriented in different directions, and those directions are identified with these coordinates. And I'm trying to find the components of the stress. And to do that, I've superposed that surface, that plane over here into the original picture. And I've done an equilibrium of forces, and I was able to determine what the new stress components are. But I've only determined one of the normal stresses. Well, there is another normal stress, which is sigma y prime. Now, here, what you can do is, as one possible scenario, what you can do is you can, if you like, go ahead and take a plane that's oriented like this. Okay, that's the plane on which sigma y prime lies, and you can go ahead and put that plane over here onto that picture. Take a cut of this now green triangle, and you can do an equilibrium of forces, and from that, on that plane there will be sigma y prime and tau xy prime. You can find tau xy prime and sigma y prime. The value of tau xy prime, of course, will come out to be exactly the same, because that's what the equilibrium of moments requires for this element, right? Just like on the original picture. Sigma y prime value will actually be different, and that value will be equal to sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 cosine 2 theta minus tau xy sine 2 theta. Okay. Now, though you could have derived it this way, there is actually a simpler way to think about this. And the simpler way to think about it is as follows. This is the original coordinate system, and there is a new coordinate system. And that new coordinate system is x prime and y prime. Presently, I'm concentrating only on that direction. So that is the direction of interest. Let me call that direction of interest A. Okay? Now, if the direction of interest could be anything, if it is in that direction, the direction of interest A is along x prime. If I choose that direction of interest to be along that direction of interest is y prime. The orientation of the direction of interest is described by the angle of theta. The difference between that direction and that direction is through an angle of 90 degrees. So if for x prime I have chosen theta, if instead my direction of interest was described not by theta but theta plus 90 degrees, then the normal that I was drawing here really would be corresponding to the y prime direction. So in other words, all of the calculations that I've done actually hold for an arbitrary value of theta, which means that if for a given value of theta I get an equation for sigma for the normal stress, which happens to be along x prime in this case, in my picture, if for theta I get this, if instead of theta into this equation I plug in theta plus 90 degrees, so instead of theta I put theta plus 90 degrees, I will get the normal stress that lies along that direction, and hence the expression for sigma y prime. Well, let us see if that actually holds, that argument. And indeed it does hold, because now if I go ahead and instead of using cosine 2 theta, I plug in cosine 2, remember here that it is the theta that I'm going to add 90 degrees to. So it's 2 theta plus pi over 2. Okay, and here it's going to be sine 2 theta plus pi over 2. Okay, now and then It turns out cosine of 2 theta plus pi over 2, or in other words, cosine 2 theta plus pi, or sine 2 theta plus pi, is equal to minus sine 2 theta and minus cosine 2 theta respectively. So don't forget the negative sign. So this is equal to minus cosine 2 theta, and that's equal to minus sine 2 theta. So my interpretation is indeed correct. You can go ahead and do an equilibrium of forces and drive that value, but instead you just identify that this normal direction differs from that direction by an angle of pi over 2, and hence instead of theta, if I plug in theta plus pi over 2, then I'll get immediately the green equation. Those are two interpretations. The second one is quicker. Now that brings me to one final remark that's associated with all of this derivation, and that remark is that remember and be very careful with the fact that in all of the equations, the angle appears with a factor of 2. So the physical rotation of the coordinates or these planes is through an angle of theta, but into all of the equations, into the mathematical description goes a value that is twice as large. Keep that in mind in our upcoming discussions.